Okay, it's time to start. Any question from this time? If not, as we said, next week we will have our midterm. So today we will teach something that's a bit hard to get taste on. so last time we finished talking about those quantum circuit, and as we say, will be to as we say, there will be you will have some questions on midterm about these quantum circuits, etc. As to do quantum circuit calculations. And anyway, so we will jump to another kind of another topic, but actually in the nature order of the book. That's about quantum universality. Okay. So basically, the idea here is we are trying to construct universal quantum circuit. So we want to find some small set of gates which that you can piece any quantum circuit together using them. Okay. And but start we go to this measurement. Okay. Because this is also part of the quantum circuit. So remember, so back in here, we say at the end of the circuit there is a measurement, and we say without, and we say something like we assume is a computational basis measurement. And so let's say that thing once again here in a bit more detail. So we say that we assume every measurement is in computational basis, because any other measurement can be constructed from computational basis measurement by you add HI and CI qubits, and you perform a unitary, then do computational basis measurement. Okay. And we have and the information of the original measurement is contained in the unitary. This is something. This is something we prove when we talk about generalized measurement. So so let's draw this a little bit. Wait, actually, I can. Do I? Oh, I don't have it. Anyway, So as we proved before, any measurement can be done with computational basis measurement. And then there is another principle that's called the principle of different measurement. That says that we also implicitly assume that we assume all the measurements are done at the end of the circuit. And so we can assume all the measurement is done at the end of the circuit, because if there is some measurement in the middle, then you can replace it with a control unitary. Okay. So the idea is this: you have some measurement in the middle, and for it to affect how your circuit goes, maybe you do some computational basis measure, as we say, so you get some 0 and 1, and you will use this classical bit 0 and 1 and to control on some other unitary. So here, for example, it control on some x. Okay, because if you don't use this to control on anything, then obviously you can just delay it to the end of the circuit. Okay, so let's assume your circuit do some adaptive thing where you do this measurement and you use this classical measurement outcome to control on something. And but we say instead of doing this, so instead of doing measurement and this classical control of x, you can just do quantum control of x and do the measurement. And it's pretty easy to check mathematically that these two will give you the same thing. Okay. So by same I mean the first line here will have the same probability of getting 0 and 1 as outcome. Okay. So here we'll also get 0, 1 as output. Right. So you will get the same probability of 0, 1, and you will get some same. I guess there's 0, 1, so let's say we condition on 0, 1, and then you will get a matrix here. Okay. So psi A, where A is depends on 0, 1. Okay. Okay. So same state here and the same probability of 0, 1 here. Okay. And then we have another principle that is the principle of implicit measurement. Okay. Okay, so we didn't talk about this here, and well, this principle says that if you only measure part of a system, then you might as well measure all the system. And this we kind of already seen in when we talk about density matrix. And yeah, so we say that at the end, if you only need measurement outcome on some qubits, so you measure here, then you can assume you will also measure the other part, because because the reduced density matrix of the, because you can think about the reduced density matrix of the measured one, so you can think about the row here, right? So everything may stay together as a pure state, but you can think about the reduced density matrix row here. And as we argued before, because by physics, these registers and these registers can be really far away. So the reduced density matrix here doesn't get affected by what you do here. So you might as well measure that. Okay. And yeah, so this seems a bit of a trivial thing, and you think about why we really want to do it. But so in the circuit, when we talk about quantum, so in the circuit PDF at the end, we'll talk about some quantum algorithm, and you see that this help you do analysis. And I guess this is kind of similar to this. So this inferred measurement is a bit of a reversal of this delay measurement, because yeah, because if you measure here, then you can condition on the measurement outcome. Right? You can condition on the measurement outcome, and then condition on the measurement outcome. Then instead of a density matrix up here, you will have some condition on measurement outcome. You will have some, usually you will have some pure state up here. Okay. So let's say outcome A. And then you can do the analysis with pure state. So yeah, so basically instead of doing density matrix, you want to deal with ensemble pure state. And as we know, pure state are actually a little easier to deal with than density matrices, just synthetically. Okay. And so that's about what we can assume of quantum measurement. Okay, so in terms of a circuit model, this means that at the end we can assume every circuit. So we can assume all the measurement are done at the end of a circuit, and we can assume every wire get measured, and you get some of your classical outcome from there. Okay, so that's about what we can assume on the measurement of quantum circuit. Any question? Otherwise, okay. So now let's start to construct our universal quantum gate, set of universal quantum gate. And okay, so what is a universal quantum gate set? It's a set of gates from which we can approximately, sometimes exactly construct any unitary. Okay. So why do we need this approximate here? This is something we didn't have classically. Classically, when we have a universal quantum gate, then set quantum gate, then we can construct any circuit for, like, we can get all the truth table correct. And so we need this approximation because we think about any unitary is a continuous set. And so, okay. And so continuous set, then if you use a discrete set to try to control everything in a continuous set, is not possible. You need some approximation. Okay. Because say here, if we have a universal gate set, it only have 3 gates, then then how many number of them you have is only countably infinite number of gates can be controlled from here. But the continuous gate, this continuous set of unitaries is uncountably infinite, so So it's not possible that you get everything here. Yeah, so you need some approximation. And anyway, so we have some examples of universal gate set. And first is C naught and every 1 qubit unitary. Okay? And this is actually exact universal set, means that you can construct any unitary exactly from here. And we just say that's impossible. Why is it possible? Because this any 1 qubit unitary is also a continuous gate set here. Okay? So yeah, so there are also uncountably infinite number of gates in this all possible 1 qubit unitary. Okay? And yeah, so this is a gate set. And yeah. And then, as we said, the most standard one people talk about is the CNA, HEDMA, and the T-gate. Okay? And yeah, this is kind of standard. And the theorem says that the approximation to every unitary is efficient. Yeah. So here we have this approximation, and we have a very famous theorem called Solovay-Kitaev. Solovay-Kitaev says that you can approximate any unitary to with this case set to some error epsilon using only polylog 1 epsilon gate. So we haven't talked about what is epsilon mean, but it is some distance measure between two unitaries. Okay. So the unitary you construct in this case set only have some epsilon error to the HOA unitary you want to approximate, and then you use polylog 1 epsilon gate. And actually this is not what Solovay-Kitaev say. So Solovay-Kitaev actually try to approximate this case set. So this case set is exact. And yeah, so actually approximate the 1 qubit unitary using those 1 qubit unitary. So this is the HEDMA gate and the T gate. And remember we have HEDMA gate and T gate here. So HEDMA gate is this thing, and the T gate is this thing. And yeah, so Solovay-Kitaev is really a 1 qubit unitary theorem. It says if you just use those two 1 qubit unitary, then you can approximate any 1 qubit unitary to precision epsilon. Okay. And yeah, so this is a really important theorem in a theory of quantum computation, and there are many generalizations. So for the example, you can think about how good. So the form H1, so how good you can approximate many qubit gate using this gate set or other gate set. And also you can think about getting better parameter on the Solovay-Kitaev. So you have a polylog here, and you want to see can you do like just log of 1 epsilon. And you can also think about what different gate set can get approximation on. Is it what other gate set? So basically, what other two gates can approximate all 1 qubit unitary, and how fast can you approximate to them? Okay. Yeah. So this is the standard universality, and this is basically the goal of this PDF. So we'll spend quite a few times how to approximate everything using this, and then we have a budget version of Solovay-Kitaev arguing why every 1 qubit unitary can be approximated by HEDMA and T. Okay, and yeah, so up here was covered in this PDF, and then we have something extra here. So special universal gate set is topology and HEDMA. Okay. And okay, and this is quite interesting for some theoretical reason. Okay. So this is actually a bit worse than the C0 HEDMA T in multiple ways. So first, the topology is a 3 qubit gate. So topology gate is harder to construct than C0, right? So remember, topology is this C0. Okay. So it's a 3 qubit gate, and the more qubit you are integrating, the harder to construct that gate. So topology is harder than C0, and yeah, so you can compare this And you see this case set is, although you only have two of them, is harder than this. Okay. And yeah, so I guess the first one of the good thing about this is so maybe I'll list a good thing here. The good thing, you only have the two gates here, and also also it's kind of the generalization of the it's a kind of like generalization of the classical universal gate, because you remember Toffoli is universal for classical. Okay, classical reversible. Okay. So yeah, so this is like a nice extension of classical computation, classical universality. Okay. But actually the most interesting thing about this is that both of those gates are real. Okay. And then you think about first, when you think about it, it's actually a bad thing, because that means this is actually not universal, right? So this is real, and every part of them is real, but you know unitary matrices are complex matrices. So how is it possible you do how is it possible for you to approximate any unitary matrix with this? And the answer is you don't. You only approximate a real unitary. Okay. And but it's possible to show that the computational power is still the same. So basically, what you do is like you say you say that you get some psi, and you can have the real part of psi and the imaginary part of psi, right? And then you encode this into some real psi, and so you can encode it into some 0 tensor psi r plus 1 tensor psi I. Okay. So you can map a complex psi to some real psi and do every computation on those real psi with those real unitary. And so at the end, when you do measurement and see some probability distribution, and you can infer that to the probability distribution for your complex computation. Okay. So yeah. And as we said, this is a special part, and this is actually both a good thing and a bad thing, because so you see the computation power here is a little restricted because you only approximate real unitary, although at the end you do measurement is the same, but sometimes you only want to deal with zero unitary, then this is good for you. Because so again, like as a theoretical tool, this shows you that you can do this, and you can do every quantum computation with only real unitary, etc. Okay. Okay. And yeah, so that's a special part about this case. Very interesting. Okay. And this is a quick overview of this PDF. Any question? If not, yeah, let's see more about quantum circuit. Okay. So those are some useful, interesting property about quantum circuit. Okay. And first is we want to say a little more about basic matrices. Okay. So we want to define function matrices, but only on diagonalizable matrices. So assume our matrices can be diagonalized like this. So summation lambda, psi lambda, psi lambda. So psi lambda is the eigenvector and the lambda is the eigenvalue. And we have some continuous function, maybe not even continuous function. So some function actually write this wrong. Okay, sorry. Oh, never mind. Oh yeah. So some complex value function from C to C. So from complex number to complex number, then we can define f of a. Okay. And yeah, so f of a equal to just you apply this function on all the eigenvalues. Okay. And yeah, so we define functions on matrices. And we also want to do this because we want to apply functions on basically the poly matrices. Or yeah. And yeah, so we have, for example, we have these Z matrices. So this is Z poly matrix, and as we all know, it is 1, 0, 0, minus 1. And when we write it in terms of eigenvalue and eigenvector, it's plus 1 of 0, 0, minus 1, 1 of 1, 1. Sorry, minus 1 plus 1 of 0, 0, and adding together with minus 1 of 1, 1. And then we think about a function of the f of x equal to theta x. So theta is just a number here. And then you will have this theta z as a matrix is theta of 0, 0 minus theta of 1, 1, because theta times 1 is theta, theta times minus 1 is theta. And so in terms of matrix is this. And okay, so here you see this definition makes sense because it coincides with what you expect when your function is multiplied by a scalar. So multiplied by a scalar, then every element get multiplied by a scalar. Okay, so pretty cool. And then we can define a real cool function now. Our function is an exponentiating function. So your f of x is e to the theta x. Then then we can define this exponentiation of a matrix. Okay. And yeah, so now things get interesting. So what's the exponentiation of matrix? And by our definition, it's just the exponentiating the eigenvalues. So 1 become e to the theta, and the minus 1 become e to the minus theta. Because 1 and e to the x equal to 1, then you have e to the theta, x equal to minus 1, you have e to the minus theta. Okay. And yeah, then it's this matrix is diagonal of e to the theta and e to the minus theta. Any question? So yeah, defining more matrices. And also you see that when f of x equal to a squared, then f of a is what you expect is a squared. Okay. So it's lambda square of this summation of lambda square, then projected onto lambda. And but you can think of this. So you think about a is some u du dagger. This is how you diagonalize a algebraically. And then here you see that every eigenvalue gets squared, so it means that this thing is the same a with d become d squared. U d squared, u dagger. And then you can insert u dagger u in between this d squared. So that's u d u dagger, u d u dagger. And this is u squared. So yeah, so you see that this do what you expect it to do. If you have your function is a square function and you apply it on your matrix and actually your matrix square. And then in general you can feel that this definition is actually linear. So and the square analysis go for any monomial. So any nth power, you have a to the nth power. So you have f is a polynomial. Then so if your f is a polynomial, this is summation some an xn, then your f of a is the same polynomial of a. It will be summation n a small a n big A to the n. And yeah, so you see this is really well, yeah. And we say so this works for any polynomial. And yeah, we skip the proof here. Proof basically only using that this definition is pretty linear. So Yeah, so you bring f of n equal to your polynomial. Sorry, f of lambda equal to polynomial of lambda, summation a n lambda n. And then you reverse the ordering of summation, you put a n outside, and you have the summation lambda of lambda n a psi lambda, and then this part, sorry, uh, then this part you use the same reasoning as before. You see this part is a to the n, and then you have summation n small n a to the n. Okay. So every polynomial then is just a polynomial of a to n, and then basically this give you a definition for every function, right? Because you can think about every function as a Taylor expansion. And, I guess we are a little circular, but here we already have a definition of every function. Yeah. But yeah, for different functions, your function has a Taylor expansion, then I guess your function, it says that if a function has a Taylor expansion, then you can express the result as a polynomial thing. Okay? And yeah, then what we want to do this is because we want to define those rotation operator. Forgot. Okay. So okay. And so the rotation operator, there are 1 qubit gates, and it's really the rotation on Bloch sphere. Okay. And yeah, so you can check that. So remember we say 1 qubit gate can be represented as, 1 qubit state can be represented as point on this Bloch sphere, this one-dimensional sphere XYZ. Okay. And oh wait, what happened? Anyway, on this Bloch sphere XYZ, and those rotation operator will actually rotate the Bloch sphere. So yeah, they will rotate the Bloch sphere and map state to state. So for example, this rotation on X will make a state on here. So you think about your rotation on X like this. Then you will make things, maybe things on y-axis to z-axis, etc. So say you rotate on x-axis by angle pi over 2, then this state will become this state, and this state will become this state, etc. Okay. Yeah, so what are they? They are exponentiating of the Pauli operator. So Rx is e to the minus I theta x over 2. And okay, and this is why we want to want this Taylor expansion, because then this tells us that okay, and so we will prove, so we will use the Taylor expansion to prove that this e to the I theta x over 2 is cosine theta over 2 identity minus I sine theta over 2x. Okay. Although I guess you can also prove false with the eigenvalue definition, but yeah. And in this matrix, and similarly you have rotation on y angle and a rotation on z angle. And you can check yourself that they are really rotation on Bloch sphere, and they satisfy some rotation rules. So for example, if you rotation on y-axis angle alpha, then rotation another angle beta, then actually just rotation on y-axis angle alpha plus beta. Okay. And so let's do some proof about why this exponential equal to this. So this is similar to, because in calculus you have Euler formula, so you have the e to the theta. Yeah, so Euler formula you have e to the I theta equal to cosine theta plus I sine theta. So here is similar, but you just have a here. Okay. And anyway, so we do Taylor expansion or exponentiation. Remember e to the x equal to summation n from 0 to infinity x to the n over n factorial. Then then we do our exponentiation of x with some exponentiation with of our matrix A, and times times number x, okay, and and we need to use the fact that a squared equal identity, which is true for every Pauli matrix x, y, z here. And anyway, so as we said before, we can do this Taylor expansion of e to the x, and so this exponentiation of matrix A, we can get the same Taylor expansion. So summation n squared, and now x is this ix, so just ix to the n here. Okay. And then we can separate into an even part and an odd part. Okay. And an even part, then we have all the scalar things, so n factorial and ix to n. And then we have a to the some even number. Then we use the fact that a squared equal identity. So a to the some even number is just identity matrix. And then on the other part, we have a similar thing. We have the summation or other thing, and a to the other power then is some even number times a, and a to the some even number times a, so that's identity times a, so that's a. Okay. So the matrix part is just identity and a here. And the number part is similar to how we analyze e to I theta equal cosine theta plus I sin theta. So you think about this and you see that's the Taylor expansion of x cosine x, and this is the Taylor expansion of I sin x. Okay. And yeah, so that's cosine x times identity plus I sin x times a. And so this proves that this thing is cosine of x actually equal to minus I theta over 2. Yeah. Sorry, minus theta over 2. I is not inside x. Okay. So x equal to, so maybe see this here, minus theta over 2 here. So cosine minus theta over 2 equal to cosine theta over 2. And you have sine minus theta over 2 equal to minus sine theta over 2, etc. Okay. So yeah, so those are pretty cool. Those are rotation operators, and by this form you can return them all really easy. So that's diagonal is cosine theta over 2. Then you have off diagonal minus sine theta over 2 because it is x, and then y is minus sine theta over 2 and sine theta over 2, and then z, this is similar to what we had before. So yeah. Okay, question? Yeah. No, yeah. And okay, so that's the background information we need to do universality. And so now we start to actually doing decomposition. So first thing we do about the decomposition is that we want to decompose single cubic gate into the rotation we just talked about is Rx, Ry, Rz. So first we start with this Zy decomposition of arbitrary single cubic gate. Okay. So we say that any single cubic unitary U, you can decompose it into 4 real numbers. I guess not really decomposing into 4. You can be parameterized by 4 real number, alpha, beta, gamma, theta. And so I start with the global phase e to I alpha, which should, well, it actually do something later, we'll see. Okay, so it's a global phase e to IC alpha, and then rotation on z with angle beta, rotation about z axis by some angle beta, and then rotation on y axis with some angle gamma, then rotation on angle z by some angle delta. So you can think about this, so you rotate a box sphere by some angle beta first, then you rotate it around y-axis by some angle gamma, so your z-axis is beyond here, and then you rotate with z-axis on some angle delta again. Okay. And yeah, this is actually we prove this by doing calculation on 2x2 unitary, but you can also kind of think this as because any rotation on this three-dimensional sphere can be decomposed into. Yeah, so this is I guess natural physics or algebra thing. So intuition here is that any rotation on the sphere can be decomposed into like a 3 rotation of the y-axis and z-axis. Okay. So this is any rotation on sphere. Okay. Any rotation on sphere can be decomposed into these 3 rotations. 3D basically. Any 3D rotation can be decomposed into these 3 rotation onto 2 orthogonal axes. Okay. Anyway, let's see a quantum proof. And the quantum proof is quite brute force. Hopefully we can skip a few details here, because yeah. And so basically you have ABCD, and then so you have a unitary ABCD, and so we kind of want to count the number of real parameter, right? So maybe that's number of real parameter. And so you have 4 complex numbers, so it's like 8, and minus, and but it's a unitary, so it constrains, and you will have 4 constraints here to constrain it down to actually only 4 of those. And anyway, we'll see how they correspond to ABCD. So what are the constraints on unitary? And so the first constraint is that so every column in the row needs to be a unit vector. So that means a squared plus b squared equal to 1. And from here, then we can parameterize a and b equal to some cosine theta, sin theta. So we can parameterize a and b into kind of polar coordinate. So a and b have some arbitrary phase, e to the I phi 1, e to the I phi 2. And but from this known thing, we know that their length square is some cosine and some cosine and sine relation. And we assume that it is cosine gamma over 2 and sine gamma over 2 because we know the answer. And similarly, then we have a squared c squared equal to plus a squared plus c squared equal to 1. And so c will have also another phase, and we put a minus sign here because we know the answer. And another sign here, right? Another sign gamma over 2. Because we have cosine here, then we must have sine here. And then c squared plus d squared equal to 1, and d also have a phase, and once again it should be cosine. Okay, and yeah, so here we already left with 5 parameters. So phi 1, phi 2, phi 3, phi 4, and this gamma parameter. And then there is another constraint that is another independent constraint that is the rows or columns need to be orthogonal to each other. So let's say about the columns must be orthogonal to each other. So inner product of the column equals 0. That means A star times C plus B star times D equals 0. And when you do that, then you see that then both of those have a term about sin gamma 2, cosine gamma 2, and the other part. Okay. And so there are 2 solutions. There is a solution of the sin gamma 2 times cosine gamma 2 equals 0, and it's special case you can deal with. And when that's not equal to 0, then you have those exponential terms that sum to 0. Okay. And yeah, so this exponential minus this exponential equals 0, and that tells you that those angle equal to those angle. Assume the angle don't change, not too different. And okay, so this thing equals this thing, and we call it beta. And then there are other independent variable on this phi. Okay. So we have one relation on this phi, and so we parameterize those 4 phis with 3 parameters. So we have those two differences equal to beta, and yeah, then we can pick. So we have a difference between phi 1 and phi 3, and a difference between phi 2 and phi 4 need to be fixed. And but the sum of phi 1 and phi 3 can be anything, and the sum of phi 2 and phi 4 can be anything. And we just say it's 2 alpha minus delta and 2 alpha minus plus delta. And anyway, now we have everything as alpha, beta, delta, gamma, and they put together, and it's this matrix. And because we have been very careful to pick everything, and you can check that this matrix actually equal to what. Yeah, you can do the hard calculation and check that this matrix actually what we claim it to be is e to the I alpha times some rotation. And yeah, I guess you can kind of see why they get a bit of feel of what is true. Say on the alpha term, you can see everything is e to the I alpha. So at least the e to the I alpha one thing is correct, and the other thing you just need to do the multiplication out to check that my claim is correct. Okay. And yeah, so sadly this is not too intuitive. Basically we count the parameters, and we see that everything that says every ABCD that satisfies they become unitary. Then you kind of using all the constraints to deduct that the remaining 4 parameters can be parameterized into this way, and you can parameterize the U with the remaining 4 parameters into this way, and it is exactly what we say. It is true. Okay, and yeah, so this is a bit of ugly theorem, but then we can use it to do something cool now. Okay, and so first we have a corollary, and that will be useful when we do 2 cubic gap. And so we say that for any single cubic unitary, we can decompose it into a funny way. So we can decompose it into a much longer way. So instead of e to the I alpha RZ, RY, RZ, we need to e to the I alpha, and some funny unitary ABC such that A times poly X times B times poly X times C, and this is equal to UN unitary, and ABC satisfies this special relationship such that ABC times together equal to identity. And yeah, so it's kind of wondering why we want this, but let's go to the proof first. And the proof is basically exactly using this decomposition here. So we already know U can be decomposed into this. U is RZ beta, Y gamma, and RZ delta. And so we set our APC such that they basically cut this RZ, RY, RZ part. Okay. So A is this RZ beta and the half of this RY. And B is negative of half of this RY, and RZ of, it's really funny, RZ of minus delta plus beta. And C is RZ of delta minus beta. Okay. And yeah, so we just need to check why this works. So why this work is so first let's see that ABC actually tends to identity. So A times B times C, and you see that so you just listen together. So this is A, and this is B, and this is C, and then you see that they cancel each other. So the RY gamma over 2 cancel with RY minus gamma over 2. So this becomes identity, and then is RZ minus, okay, so this is very confusing. So RZ of minus delta plus beta over 2. and then we have this delta minus beta over 2. And so I believe delta cancel each other, and then we have 2 of minus beta over 2, so this is minus beta. And yeah, then you see that this is just RZ beta, RZ minus beta, so this equals identity. And then why does it back to U? So basically back to U, we need to analyze what is x beta x part. Okay. Sorry, not x beta, x part. So if you sandwich B with x and x, and I claim that it actually give you negative angle here. And that's because if you have a sandwich x and some function of y, and so you essentially sandwich some function of y with x, actually equal to a function of minus y. Yeah. And that's actually all come from xy anti-commute. Okay. And so xy anti-commute, and then if you multiply 2x on the right hand side, multiply x on the right hand side on both equations, and you see when you sandwich y with x, you get negative y. Okay. And then you can think about this sandwich f of y with x, and assume f is a nice function, so we can do Taylor expansion. Then this y is the Taylor expansion of this poly y, so it's a polynomial of y, right? Summation an y to n. And then you can, for every y to the n, you can stick x squared inside, because x squared is identity. So you can sandwich every y here. It's xy x to the n. Okay. And then as we know, xy is equal to minus y, so this is just summation an minus y to the n. And so that's f of minus y. And so similarly, you sandwich this f of z with x, you get f of minus z. And so yeah, so what happens when you sandwich this rotation of y, which is rotation y with angle and rotation z with angle? Well, this is a function of sigma y, and this is a function of sigma z. And so xbx is really, so once again, you can insert the x squared between these ry, sorry, here. You can insert the x squared between these ry and rz, and you get x ryx, x rzx. And so as we know here, you will get a negative sign on y, and I really just give you the negative angle, okay? Because, okay, so want to see that, we need to go back a little bit. And yeah, so our y is this thing, so if you get a negative sign on y, then you basically get a negative sign on theta. And now z is this thing, so you get a negative sign on z, you are getting a negative sign on theta. Okay? So f of minus y, so f of minus y becomes, so is ry of negative angle, so you get negative sign angle, negative sign angle. Okay. So this is gamma over 2 and delta plus beta over 2. And finally, you piece it together to your e to the minus I alpha a, x, b, x, and c. Then you list them together, and you see they combine nicely to what we want. So it's gamma over 2 and gamma over 2 combine back to your ry gamma, and this delta minus beta and delta plus beta and delta minus beta just become delta over 2. Yeah. Okay. And as we said, this is the decomposition of our unitary. So yeah, so this is our unitary. And yeah, we are about on time, so let's have a 10-minute break, and then we will see how we get any control unitary from this decomposition. Okay. respect to quantum universality. So we have this interesting decomposition of decomposing a unitary U equal to e to the I alpha ax bx c, where a, b, c are single cubic unitaries multiplied to identity. And this gives us a way to do arbitrary 2-cubic control operation using only C naught and arbitrary 1-cubic gate. Okay. So we want to do control unitary like this. So some single cubic unitary U here, and we want to do a controlled version of it. And we say that it is equal to this gate. So we have our ABC here. So ABC, and then you have this control, you have those C naught in between, and then you have this this kind of phase gate. So this is like some Z rotation here, e to the I alpha, and yeah, that's equal to e to the minus alpha over 2 and e to the I alpha. And yeah, and this ABC is the decomposition we're talking about. So U equal to e to the I alpha x bx c. And so why does this work? Because you can think about what is this thing do when the first cubic is 0 or 1. And when the first cubic is 0, then the C naught doesn't do anything. Oh, yeah. So C naught here doesn't do anything. So the second cubic you just have ABC. Okay. And remember, so the tan on the circuit go from left to right, and when you do calculation you go from right to left. So this ABC here is ABC here. Okay. So anyway, so when you first cubic is 0, then C naught doesn't do anything. So you have ABC here, and as we say, it's identity. And when first cubic is 1, then your U is, so on the second cubic is basically this A, then C naught will become X, so you have A, X, B, X, C, and then also you have the global phase that only do, okay, oh, I forgot to say about the phase, okay, so when C naught, when the first cubic is 0, then you hit it with 0 here, and you hit this 1 here, and you have phase. And then when the cubic is 1, then you hit this e to I alpha, and you get the e to I alpha phase. Okay. And also something special is that this phase here, this is actually non-trivial, okay? Because you have a control phase, so this is not global phase. This phase only happens when the first cubic is 1. Yeah. So yeah, so this part is in terms of a control U, this is non-trivial. So you need to keep it in a decomposition, and it's represented in this extra basically Z rotation gate. Okay, so yeah, so this is how you do control unitary, and so this is one control, and we found out that we can do arbitrary control. Okay. So we can think about we want to control on n different qubits. Okay. So we have this Cn, C to the n, U, and it should control on, so it should be n plus 1 qubit gate, where you control on the first n qubit, and you do U on the last qubit. And you can write it in this way. So if the first n qubit is in some computational basis x1 to xn, and the target is in some side, then the control qubit still the same, is still x1 to xn. And you apply U to the x1 times x2 times xn. Okay. So this x1 to xn, and then this one x2 to xn is not different. This is an n-bit string, and this is x1 times x2 dot dot times xn. So this means that this is a number between, or this is a number of either 0 to 1 and equal to 1 only when all those xi are 1. Okay. So U to all those side. But anyway, this is just a complicated way to say we control on the first n qubit to apply U. So only when the first n qubit are all 1, you apply U on your side. Okay. So think about this thing. I guess we didn't really say side. Never mind. Yeah, it should be 1 qubit, although we draw a lot of line here. So that's just a little bit of confusing, but I think for our construction, it's only one line here. Okay. But yeah. Okay. And we say that this can also be controlled from the same set. So C naught and any single cubic unitary. Okay. So for any single cubic U. I guess, okay, so this is a little confusing. So the definition here we define is U to can act on any number of qubit. But for the claim here, we restrict U to be single qubit. So that's okay. But anyway, oh sorry, I'm saying I'm skipping my ahead a little bit. Okay, and so first we want to prove is that so you only have two control here. Okay, so I'm skipping one zero here. Okay, so we have a claim here saying that you have two control. So we had how to control one control unitary. So we say we can control any two control unitary from the same set. So only C naught and a single qubit unitary. And the proof here, well, we list the result here, and I guess you can check it at yourself at home. Okay. So we say this is how you control the control U. So you have some C naught, and so it's controlled from the control V. Okay. This is come from, we say we can do any control unitary. Okay. And so we need to have a control V dagger, and control V. And what is V? V is like a square root of U. Okay. So unitary, you can always think about, you take a square root of our eigenvalue, then you get a V such that V squared equal to U. Okay. And yeah, so you have the V such that V squared equal to U, and then you have this control on V, and you can check yourself that this thing is control U. Control U. And I guess, so for example, a really quick check is that you have a 0 here and a 0 here, then none of those control do anything, so you have identity as expected. Right. And yeah, so you can check all four cases to see that this give you control U. Okay. Okay, so from the control U, then we can do the thing we say we want to do. So we will skip ahead also. And the corollary of this, then you can do this very interesting gate, that's Toffoli gate. Everything that is useful in also things kind of reversible gate that we can buy, for example. So yeah, Toffoli is control X. So it's a special case of this. So you can do Toffoli with C naught and arbitrary single qubit unitary. Okay, and yeah, so back to check. Then we want to do control NU for any single qubit U, CNU. And once again, we have construction here, and this construction is easier to verify. So, but we need to use a lot of ancilla. So we have a whole bunch of control. So those you have N control here, N qubit here, that's your control, and here we just N equal to 4. And then we need some ancilla to do some ancillas that we actually get returned to the starting state. Yeah, so those are HR space that you store intermediate computation, and then there is target qubit. Okay. And so what we do is we start adding or multiplying the controls into ancilla. So yeah, so as we say, we can do Toffoli, and so when you do Toffoli on the first 2 qubits to ancilla, and the ancilla are starting with O0 and they will end with O0. So you Toffoli the C1, C2 ancilla, then you will get C1 times C2 here. Okay. So this is 1 only when both C1 and C2 equal to 1. That's what is control do. And then you control the C3 with the first ancilla to the second ancilla, then you get C1, C2 times C3 here, because you have C1, C2 here, and it will times C3. And then finally here you get C1, C2, C3 times C4 here. and then you just get a control unitary here. As we know, we can do control unitary on your target, and then you uncompute all the NC, okay, to return the NC all equal to 0. And also there is something special that okay, so you can check in some special case to see that uncomputed is necessary, right? It's actually necessary, so it's not just to return the NCR to 0, although that's one of the effects. And so if you don't do the uncompute, then this is not the gate you think you want to do. Because if you don't do uncomputation, then you are left with very likely to left with entanglement between control and NC-la. And NC-la without doing this. Okay. You can check it out, say if you have like some plus state here and you add to here, then you will get entangled. And so if you don't uncompute it, your state will have entanglement to some extra thing. Then you have entangled state to a bigger space, then actually get then your density matrix. So you think about what the state on the target and control, you get some density matrix. That's obviously not the pure state you expect you get, right? So you apply this gate. You have a pure state input, you expect a pure state output. But the output state is entangled to some other thing, then you actually get a mixed state. So obviously that's not the correct answer. Yeah. And yeah, so if you don't compute, you have entanglement between control and NC-la. And NC-la. So, yeah. Compute. Okay. So that's something important. Question? No. Okay. Then we go to, okay, so we don't have that much time, so let's try to go really quickly. So that's the some gates we can control, then we go to more serious about control our universal quantum gates. Okay, so we want to show that our Han-Hsuan and CNA is a universal gate set. Okay, and so there are 3 steps. So first we show the set of any unitary on 2 computational bases is the exact set, and we'll see. So this is some really weird unitary, and we'll see more precise definition later. Okay, and then we say that all single qubit unitary, you have an all single qubit unitary, then basically we can approximate, you can exactly compute this thing, and together with C0. Okay. And so yeah, so we will show that all single qubit unitary, and C0 then is a universal gate set with exact. That's exact. You can control everything, any unitary exactly. And finally, we say that Han-Hsuan T. So the Solovay-Kilov theorem, we say Han-Hsuan T can approximate all single qubit unitary. So Han-Hsuan T and C0 is universal. And yeah, so let's see what this weird 2-level unitary. Well, it has 2 levels, so it's a unitary that's really close to identity matrix. So you have a whole bunch of 1 on the diagonal and 0 otherwhere, except for those 2 levels. So we will pick some S and T, and on those S and T, okay. And on those S and T is you have embedded unitary, some unitary U tilde here. It's on ABCD, that's your unitary. So yeah, so those 4 points is ABCD. Okay. And so first we show that if you have you can do any 2-level unitary, then you can get any unitary. So And that's kind of like Gaussian Gaussian elimination. So let's see how we do that. So if it's on unitary, for example, 3 by 3, so you have those 9 parameters here. And we want to show that you can have 3 two-level unitaries such that you multiply them together, become this U. And we can do this calculation in backward. So we want to find U1, U2, U3 such that you multiply them on your U, become identity. And but those are unitary, so you can do inverse of them, which are the dagger. So U will equal to U3 dagger, U2 dagger, U1 dagger. Okay. And so obviously you have two-level unitary, then U dagger is a unitary. So this in dagger is still two-level unitary, pretty obviously. But anyway, so let's see the more important part, how you find U1, U2, U3. So say we want to do Gaussian elimination kind of stuff. So we want to multiply U with a two-level unitary such that this B will become 0. And okay. And so if B is already 0, then you do nothing. And if B not equal to 0, then you have this two-level unitary. So you have this, okay, so S and T are here. So you have those 4 elements that depend on A and B. And you can check that it's a unitary. Okay. And yeah, then you find out that you multiply this on U, and I guess the second, sorry. Oh, yeah, so you multiply this on U, and you will see that because you have B and minus A here, and so on this 2-1 register here, you will have AB inner product with this B minus A, and they become 0. Okay, and yeah, so this register will become 0, and the other A register will be whatever. We don't really care. Okay, so you multiply U1 on U, you get a 0 here. And yeah, and then you want to make a C prime into a 0 now. Okay, and so we want to make a C prime equal okay, sorry. You want to make a C prime equal to 0 and A prime equal to 1. Okay, and that's possible because you apply this unitary. So if C prime is already 0, then you just multiply the basically inverse of A prime, and then A prime, this will become 1. And if C prime not equal to 0, you apply this matrix. Okay. And so once again, by a similar argument, you will see that the C prime register will become 0. And also you will see that on the middle row you have this 1. So this 0 is not affected, so this will stay 0. And you will get this matrix. So 1, 0, 0. Okay. And other 16. And but here the interesting thing happened is that we know this is still a unitary matrix. And you have 1 here, so you consider first row. So you consider the first row here. Then the first row is the unit vector by value 1. So the D double prime and G double prime must be 0. Okay. So we see that your matrix actually look like this. And you have a 2 by 2 matrix here, U prime. And yeah, and this also needs to be a unitary matrix. And so you can find, you can just set your U3 as the dagger of this matrix because it's already 2 by 2. So if you have 1 U dagger here, it's also a 2-level unitary. Okay. And yeah, so that's where our U1, U2, U3. So you find the U1, U2, 3, such that multiplying them together with U, you get the identity. Okay. And you can kind of feel that this method is very general. So we get this on the example of 3 by 3. And you can get this recursively, right? In general, we can do induction, and we say 2 by 2 unitary. Obviously, you can find the U dagger as a 2-level unitary, as its inverse. And then you can get, if you can do D minus 1 times D minus 1 level unitary, then you can always then Then given any d by d level unitary, you can always reduce the problem to this d by 1 by d by 1, because you can get some u1 to u d minus 1 to do the Gaussian eliminations kind of step. So you turn all those values to 0, and as we know, this will turn all those to 0 as well, because if this is 1, then all those must be 0. And yeah, so you reduce your problem to this block diagonal form, where the extra dimension is just 1 now, and then you get d minus 1 by d minus 1 level unitary, d minus 1 by d minus 1 unitary u prime here, and yeah, and we say that we can already decompose those equal to level unitary, so you can decompose also d by d unitary into 2 level unitaries. Okay. And yeah. And so you count how many unitary you need to use, as it is recursive. So from level d to level d minus 1, you need d minus 1. And d minus 1 to d minus 2, you need d minus 2, etc. And you add them together, then the number is this quadratic number, d times d minus 1 divided by 2. And so as a corollary, you want to do n qubit, then d equal to 2 to n, then you need a lot of unitary. So this is exponential number, 2 to n minus 1 times 2 to n minus 1 minus 1. And yeah, it's exponential, but it's doable. Okay. Yeah, it's expensive, but it's doable. So, okay, so that's the first step. Then second step is we want to say single qubit unitary plus CNOT is universal. Okay. And yeah. So we already said that 2 level unitary are universal. Now we want to decompose arbitrary 2 level unitary into single qubit and CNOT. Okay. So remember our arbitrary 2 level unitary is this. So is u, and it acts on level s and t, and on s and t is on unitary u tilde. Okay. And so basically we think about u tilde is on 2 by 2 unitary, right? So it's kind of like single qubit unitary. The single qubit unitary is 2 by 2. And yeah, so actually get this u tilde single qubit unitary and try to transform it into this 2 level unitary on level s and t. And so what we do is we apply u tilde on the first qubit, and then write down the matrix. It will like this. It will be this. Oh, actually it is wrong, but wait. Single qubit. Okay. So here is a bit wrong. Okay. So we have this is you have control to the n and the u tilde on the first qubit. Okay. And it will be this thing. Yeah. Yeah, it will be something like this. Yeah. So anyway, so we'll start. And okay. So we need to use something we know before. Okay. So if you do multi-control of so we want control on all other qubits and apply u tilde as a target on the first qubit, and it will look like something like this. Although I guess a little weird. Yeah. But I guess anyway, this is some intuition. This should actually look like this u tilde. because control is only when all other qubits are 1. So you have your identity here, and yeah. So actually it should look a little different. So you should have identity here, and let me write a little more careful, so this is not correct. So you should have identity and utility. Okay. And anyway, so this look a little like this, but you want to swap things around to actually have your utility on SNT. Okay. And we'll show down time. Anyway, let's go really quickly. So we'll do some funny thing that's called gray code. So we'll move these S and T kind of together in terms of bit string and do some multi-control unitary. Okay, so we think about those coordinates. We are on n qubit, so we list them into bit string, right? So S is on bit string and T is on bit string, and the bit string are going to be different, multiple bits. And so we want to bring them together, so we just flip the bits one by one. So for example, S here and T here, you see that they are different on 3 bits. Then we can flip them one by one. So we go from this G1 to G4. So we flip this bit, and then flip this bit, and then flip this bit, and you will see that you will change S to T. And this sequence, we give a name like G1 to G4. Okay. So we can always find this sequence G1 to Gn, such that G1 equals to S and Gn equals to T. Okay. And so the idea is we change the basis from G1 to Gn minus 1. And so this S will be bring to some string that's just 1 bit away from T. And so if you control on any color qubit, so S and T is just different on 1 bit. So if you control other bits as those things and do a multi-control unitary, then it will be something like this. Yeah. So I guess what I want to say is when S and T are just different on 1 bit, then you can do a multi-control utility. You can control on all other bits and do a utility between S and T on this bit. And then you will be the 2-level unitary you want to do, and then you can flip your basis back. Okay. So you can bring G1 to G3 here and do a control unitary on the second qubit, and bring G3 back to G1. And so that will be our 2-level unitary. Okay. And yeah, so we see that. Okay. And yeah, so how we do the change of basis is like, so for example, we see G1 and G2 is only different from this bit. And so you control on all other qubits equal to those things. So you do a multi-control the X on the fifth bit. So you control first qubit on 1, second qubit on 0, third on 1, and fourth on 0, and next on 1, and flip those qubits, then that will flip the G1 and G2, and etc. Yeah, so for example here, so you want to flip this thing, and so you control all other bits equal this thing, and you do X on the fifth bit. Okay. And also you can control on 0, as we said before. The control on 0 is this circle thing, and it's control on X, control on what, so control on 1 you sandwich with X gate, you get control on 0. Okay. And yeah, so you get those swapping around, and you get some permutation between the bases. And let's keep the detail. And as we said, at the end you bring the G1 to Gn minus 1, and as we say, you bring G1 to Gn minus 1, and then you do your utility on the deferred bit. So maybe let's see an example. And so for n1 equal to 3, and we have the first way example. So we have your 2-level S and T is 0, 0, 0, and 1, 1, 1. Okay. And utility is on ABCD. Okay. So G1 equals 0, 0, and Gn equals 1, 1. And our gray code look at this. So you play 1 bit by 1 bit. And so we have our code. So first we have the swapping between G1 and G2. So you will flip the third bit and the controller first 2 bit equals 0, and you flip the second bit. Say flip the second bit, control on this being 0 and 1. And apply the U tilde on the first bit, control on the other 2 bits 1 and 1, and then you flip the basis bit. So that's how we do arbitrary 2-level unitary with those multi-control gate. And yeah, so that's why we talk about multi-control gate in the last class. That's how you use CNOT and arbitrary single qubit unitary to get arbitrary 2-level unitary. And yeah, so this proves that CNOT and the single qubit unitary are universal. Question? Yeah. And yeah, so you can do counting and you find out that they use a lot of unitary. So so every multi-control you need to use order n gate, and every 2-level unitary you need to use order n square gate. and so each unitary you need to use exponential number of 2 levels, so 2 to the 2 to n. So so totally you need exponential number of gate to approximate arbitrary unitary, but it's doable. Okay, so I guess this part of approximation is actually pretty efficient. You only need polynomial in number of qubits, but to approximate each arbitrary unitary with 2-level unitary, you need a lot of gates. Okay. Oh, we're pretty fast, so maybe we can finish this today. Okay, so finally we get our budget version of Soleil Kitayaf. So I want to say, K0 and T can approximate any single qubit unitary. So the short answer is well, you just look at the nice papers all the way in the Kitayaf, and they say that you can use polylog C, polylog 1 over epsilon gate. Okay. And the long answer is we'll have not quite good proof of why this is possible. Okay. And so first we want to define a distance on our unitary. So what do we mean by epsilon approximation on unitary? Well, to define a distance on unitary, we get a norm on unitary. So we want to say, well, 2 unitary are same. It should be when their difference equals 0, right? So we put a norm on their difference. So we think about how big is this matrix that's U minus B. So we want to say how far away are U and B. Okay, so we have a norm on U and B. And but for a matrix, there are a lot of ways to define its norm. Okay, and yeah, like say you can have like a norm square of your. You can put a norm on every element, or you can put a norm on its eigenvalue, etc. But anyway, here is the norm we pick. We pick the spectral norm. So we say the norm on this difference is the so it's basically a maximum eigenvalue. We say is this is the norm of this vector. So basically you look over all unit vector. Okay. So you apply this matrix on any unit vector, and you see what's the maximum value, what's the maximum length you can get. And yeah, so this is called spectral norm. And it's basically the largest eigenvalue of this matrix, if it's diagonalizable. So it's the largest eigenvalue. You think about it. And yeah, and it has many nice properties. For example, it's unitary invariant. So meaning that you multiply this by any other unitary before and after it doesn't change. And so that's pretty obvious. and then it also has triangle, inequality, etc. So a lot of things you expect from a norm. And also, I guess the most important thing is that two matrices are equal to each other, so U equal to V if only if the norm equal to 0. Okay. So it looks like a norm. Okay. And then obviously you can choose many different norms for yours as a distance real theorem, and I guess there are some arguments to say the spectral norm is the correct one. Let's skip that. Anyway, let's go back to our budget solar kit app. Okay. So, and so now we want to do rotation. Okay. Now, basically, we want to analyze this as a geometry on our block sphere. Okay. And so we have a generalization of the rotation x, y, z. Now we want to rotation on any angle. So remember, we can have like poly on any angle, on any direction on our block sphere. This is n vector dot sigma. Okay, so we want to rotation on this n direction. We define this rotation, and it's defined as this exponential way, just as usual. So e to the minus theta minus I theta over 2, and your poly on the direction n. Okay. So remember, before we have x or y or z here, but here we say we can want to do rotation on any direction. So this will rotate on this nk direction with angle theta. Okay. Okay. So back to our universal case A, we really only have 2 gates, right? So only have Hedema and T, and there are not much we can do. We can do like basically alternating between them. So it's Hedema T, and well. And but what's interesting here is that so think about what's T on this block sphere. Then you can do calculation, and you can show that it's in some direction and some angle, but the exact number is not important. What's important is that they are irrational. Okay. Because an irrational number here. Okay. And so here first we use that theta is irrational. Okay, theta irrational is the important thing. Okay. Because I guess here irrational we actually mean irrational multiple pi. Okay. Because theta equal to 2 pi is actually like 1, right? Because theta equal to 2 pi is 1 circle. So we want to say is the irrational fraction of a number of circles. Okay. So theta is irrational multiple of pi, and this means that you just keep doing this. So this HT, and you have it many times, then you can actually get. So this is something hopefully you learn in calculus. Then is so you do this HT to arbitrary times, and it's actually dense between this whole circle from 0 to 2 pi. Right? So it's a rotation, so this angle is between 0 to 2 pi, right? 0 to 2 pi. And by keep rotating, but it's irrational, so you never go back to itself. So, and you will densely populate this number value between 0 and 2 pi. And that means that you can approximate the rotation around this angle n to any precision. Okay. So you have any Rn of alpha, you can just do Rn of k theta for some maybe very large k. Because theta is irrational, so those k theta will be dense on this circle. Okay, so that's something interesting. And so that's some angle, then basically we just need to find another angle. So so we have this, so if we sandwich Rn theta with Hedema, so basically that's Hedema T, and we will get Rn theta for a different, so for a different direction n. Okay. So, sorry, so I say this wrong. So n is not really irrational. So n is just on the direction. Here we just have theta irrational. Okay. theta irrational. And yeah, so TH is another direction and with basically a sin theta. But once again, the theta is irrational, so you can approximate any rotation around this M angle. Okay. And yeah. And so that's basically the end. We are super fast. We have extra time. Okay, so let's get a little slower. And yeah, so let's get a little slower. So what we want to do this full thing. Okay, so we want to do this alternating thing. So we kind of ask, why don't we just do like h to the k, right? So we want to do this alternating because you think about h to the k. Maybe I should write, I guess it's okay here. Let's write lower part. Okay. So here the important thing is that we can get irrational number, irrational theta here. Because you think about if you just do h to the k, then this one will not give you the same effect because we know h squared equal to identity. So h is like a rotation of angle pi. So yeah, so h squared equals identity, so h to the k will just be h or identity. Right? So you only get two possible angles. Yeah, similarly, t equal to, I think it is 1, 0, 0, e to the minus e to the I pi over 4, plus I pi over 4. And yeah, so similarly, t you also have the rational pi angle here. So like t to the 8 equal to identity. Okay. So t also only give you 8 possible angles. So h only give you 2 possible angles, t only give you 8 possible angles. But if you alternating between them, then you see that you actually get some irrational angle. So HT give you some irrational angle, and this thing basically TH give you also the same irrational angle, but on a different axis. And what's important is that you have two fixed axes here, and they have some constant degree between them. So you have some n, and you have some m. Maybe let's draw here. Yeah. So I don't know. So you have, I don't really know where they are, but just schematic. So you have some axis n and some axis m, and you can do arbitrary rotation around them. And they are claimed that. So similar to the widely decomposition, then just because you can do arbitrary rotation on n, arbitrary rotation on m, then you can do all possible single qubit unitary. Yeah, and I guess ignoring the global phase, global phase on single qubit unitary doesn't mean anything. Yeah, so you can do arbitrary single qubit unitary. And here there is something funny. So here the book is actually wrong. Okay. So book says that you can do this with 3 of them. So when you have y and z, I say that so arbitrary rotation on sphere you can just with 3 rotation on y and z axis. You can do z rotation and y rotation and z rotation. And yeah. But the book says you can do n rotation, n rotation, n rotation. That's actually wrong because it's possible to do only 3 of them with y and z because y and z are orthogonal to each other. And n and m are actually not orthogonal to each other. They have some angle between them. Yeah. And so when you think about it, the smaller the angle of those things, then you actually need a longer sequence to do arbitrary rotation on the sphere. Okay. Yeah. So book has a quadrant saying that you can use 3 rotation to do this, but that's not quite true. And so actually depends on the angle here. Okay. there's an angle theta here and the length of the sequence. So length of the sequence. Maybe write it down here. Okay. So you need to do a lot of rotation. You need to do Rn, maybe Rn. And the length here is about order 1 over theta. Okay? So the smaller the angle is, the longer sequence you need to do. Okay? And yeah, so the YZ you can do with only 3 because the angle is basically the largest possible circle. But anyway, this theta is some fixed thing, right? This theta doesn't depend on well, there is no number of qubits. But theta is just a fixed number that you can calculate from H and T. It's some constant number, and so yeah, so the angle is angle between them is a constant number, and so you do constant number over those rotations, and you can approximate any single qubit unitary. Okay, and yeah, and this is a budget version because so we keep the epsilon calculation part, but if you calculate the epsilon here, you see that you actually need omega 1 over epsilon number of gates. So this is actually worse than the solar wave Kilaf we can, right? So solar wave Kilaf we say can do order log, polylog 1 over epsilon, so you have extra log here. But here the approximation you need order 1 over epsilon gate. So it's a worse approximation, but it gives you some idea about why this is possible. And I believe the Y epsilon can kind of come from here. So if you want to approximate the angle to approximate some angle to order epsilon with this kind of thing, then you need like 1 over epsilon number of k here. Okay. I believe k is like about order 1 over epsilon, and that's why, and you get the omega 1 over epsilon. Okay, so we are actually ahead of schedule, but I think that's fine. So we'll stop here now if you have no question, and next Tuesday we'll have midterm review, and Thursday we'll have our midterm. Okay, so yeah, see you on Tuesday.